So in this section, we're going to be learning how to solve let me start off with my differential equation. x1 prime equals ax1 plus bx2. x2 prime equals cx1 plus dx2. Okay, now you're going to remember that the solution is going to be parametric. And in fact, method 1 is we could actually convert to a second order dE, and then we could solve using chapter 3 methods, because we already know how to solve a second order differential equation. And in fact, there's another method, method 2. We could take, thinking of these as x and y, you could take dx2 over dx1, right? As cx1 plus dx2 divided by ax1 plus bx2. And then this happens to be homogeneous from chapter 2, but that's a little harder to solve that way. Okay, so what we're going to be looking at is a direct method, method 3. This is a direct method. Okay, and so the idea behind this is we're going to start this much the same way we started in chapter 3. I'm going to take my ansatz, to be x of t equals e to the lambda t times vector v. Okay, and just to write that out, if you want to write that in components, that's x1, x2 of t, right, equals e to the lambda t times v1, e to the lambda t times v2. Okay, so that's what it looks like in parametric form. Okay, and now we want to substitute into the equation x prime equals the matrix A times x. Our matrix A is that 2 by 2 that we started with. I'm just going to leave it in this form for a second because it'll be easier to do our substitution. If we take x prime, right, the only thing that has to do anything with t is this term right here. So the derivative with respect to t will just be lambda e to the lambda t times v. Okay, and then on the other side, a times x is going to be a times e to the lambda t times v. And this is a scalar, so it can come out. And so we could write that as e to the lambda t times a times v. So this is a matrix times a vector. Okay, now if I put x prime equal to ax, I get lambda e to the lambda t times v is equal to, there's my other expression, e to the lambda t av. Now e to the lambda t is a scalar that is never 0, so we can just take e to the lambda t out. And so I'm going to rewrite this because it's usually written in the other direction. And I see that a times v must be equal to lambda times v. And couple things to notice here is that both the v and the lambda are unknown here, right? And this equation right here is very special. This, in fact, is the definition of what's called an eigenvalue and an eigenvector. So let's go ahead and define that. Definition. In fact, A could be any square matrix. Let A be a matrix, an n by n matrix. We're going to only work with 2 by 2s, but that's fine. We could just define it for n by n. If there is a scalar, lambda, and a vector, I'm missing an important word, and a non-zero vector, v such that a times v equals lambda times v, then lambda is called an eigenvalue from the German for a, and as we're going to see, v is an associated eigenvector. Okay, good. So those are terms that you're going to hear bandied about quite a bit. And so again, this is just the general definition. Now for us, let's be even more specific, because our matrix A is actually just a 2 by 2. For us, we'll have a times x1 plus b times x2 equals cx1 plus dx2. So this is my a times x here, and on the other side of the equation I'm going to have lambda times v, right? So that's just going to be lambda times x1, and oops, these are now, let me change those to v's. Sorry about that. That's AV1 plus BV2, CV1 plus DV2 is lambda V1 and lambda V2. Good, so this is what I'm trying to solve, and both lambda V1 and V2 are unknown. Whoops, unknown. Okay, so let's see if we can solve for those. So I'm going to go ahead and bring the lambda over to the other side, so I'm setting my equations equal to 0, and so I'm going to have a minus lambda times v1 plus bv2 equal to 0, and then cv1 plus d minus lambda v2 equals 0. And this equation is going to be very, very important to remember. So let me star that, because this is the equation we're going to use to solve both lambda and v1 and v2. And then it's just important to remember how we got there, right? From our definition, we can just subtract lambda from both sides. Okay, so what is this? This is two equations and two unknowns. Notice we're setting it equal to 0. Remember that we have three possible outcomes for a system of equations like this. Number one is we have a unique solution. If we had a unique solution, what would it be for v1 and v2? If we had one, then the unique solution, unique solution is v1 equals v2 equals 0, right? Well, what we said was we don't want v1 and v2 to be equal to 0, so we don't want that case to be true. So what does that leave? Either no solution, but we know that there's always a solution, so that's also not the case. No solution is also not possible. So therefore, the only case that's left is an infinite number of solutions. Okay, what does the infinite number of solutions mean? This means that they are the same line, right? And so how do I guarantee that my two equations are the same, are just multiples of the same line? Well, we saw that in Cramer's rule. So from Cramer, maybe I should write this in white here, so it's a little bit easier to read. So from Cramer's rule, the denominator is the determinant of a minus lambda b c d minus lambda. Now, if I were able to compute this in my denominator, in other words, if this is not equal to 0, right, then I could use Cramer's rule to solve this for v1 and v2. And so what I need to do is I need to say that this is 0, so that I'm forced into this situation where I have an infinite number of solutions. Okay, so if this determinant is equal to 0, then these two lines are actually multiples of the same line. Okay, and so in order to solve this equation, then we are forced to say that the determinant I'm going to rewrite it a little bit differently this time just to make it a little bit easier to read. The determinant must be 0. And so this is the second equation that we need to remember. Okay, and this equation actually has a name. This is called the characteristic equation, which should sound familiar because we used the characteristic equation in chapter 3. And in fact, we're going to see later that the characteristic equation from chapter 3 is the characteristic equation that we have right now. Okay, so I'm at about the 10-minute mark, so I'm going to stop here and I'll restart in the next video. See you then.